Hi everyone, my name is Linh Bui. I would like to present with you about validity and reliability. What is, how can we measure these concepts, and how can we ensure validity and reliability in our study? In short, validity is about answering the question whether we actually measure what we are intending to measure, whether our findings are accurate or close to the truth. Reliability is a little bit different. We concern about the reproducibility of our study, whether someone else using the same method in the same circumstances would be able to obtain the same findings as ours. So first, let's jump into an example of studies which are neither valid nor reliable. First, we have a set of 3 children, 1, 2, 3, and we know the true body weight of these children. But we can see that the recorded results from the data collectors is different from the true body weight that we know. Sometimes it's higher, sometimes it's lower than the true values. So we can say that the results we got from the data collector is not valid because the results do not represent the true body weight, and they are not reliable as well because they are sometimes too high and sometimes too low, and the relative difference from the true body weight vary from child to child. In another example of 3 persons ABC, we know the true smoking status of these people, but the recorded results from the data collector is different from the true value. We can see that for the person A and C, there is misclassification. So to visualize the concept of invalid and unreliable results, we can use a figure on the left. So the innermost circle represent the true value that we want to measure, that show the validity of the study, and the outer circle show the reliable, the variability of the obtained uh, results. So in this case, we can see that the dot, which is measurement, scatter around all circles. So we have no valid or nor reliable in this case. Let's talk about another example of study which are not valid but reliable. In the example of the 3 children, 1, 2, 3, and we know the true body weight of them, we can see that the recorded result of the 3 children are consistently 2 kg higher for every child. So in this case, we can say that the results is not valid because the result again do not represent the true body weights. However, they are reliable because the results are too high, are consistently 2 kg higher for every child. In another example of clinical trial, we can see the true effect is different from the observed effect with differential loss to follow-up. This is maybe because patients who are lost to follow-up is likely have more severe health conditions. So in this case, the measurement in our study with a patient who stay can still be reliable. But our result overall is not valid because we cannot evaluate the patient who are lost to follow up. So in the figure on the left, we can see the dot in not concentrating on the innermost circle, but in the outer circle. The dots are clustering together, which show the reliability of the measurement. So in this case, the research method do not hit the heart of the research aim, which is the truth that we are trying to obtain. But the repeated attempts get almost the same but wrong results. An example of the study which is fairly valid and not very reliable. We have the data on the same 3 children. But this time we see that the recorded result is sometimes lower, sometimes a little bit higher than the true value. this result is fairly valid because the results are almost representing the true body weight, but they are not very reliable because sometimes the recorded results are higher, sometimes it's lower than the true value. So in the figure on the left, we can see that the dots are getting closer to the innermost circle, but they are still scattering around. So it is an example of the research method hit the aim of the study fairly closely, but repeated attempts have very scattered results, which is not reliable. Finally, we jump into the case that we should be looking for the study which is reliable and valid. In this case, we see that the recorded results and the true body weight are 100% the same. And in the figure, we can see that on the dot, which is measurement, like concentrating on the innermost circle. This shows the research methods hit the heart of the research aim. We measure what we are intending to measure, and the repeated attempt on hit the heart, like the repeated measurement, are the same. So we can understand validity as bias or systematic error. That show how far the measurement from the truth. Some example of bias would be white coat hypertension or cuff size or arm size which apply to all patients. For example, in a study, all the patients in the study can endure the white coat hypertension. About reliability, we can understand it as variability, spread or dispersion among measurements. It's like finding the difference between repeated measurements. We can see this random error through some example like measuring blood pressure of patient in different positions, sitting, lying, standing, or measuring blood pressure of patient in different of time during the day. So we just walked through the definition of validity and reliability. Now we will see how we can measure these concepts. Measuring validity and reliability is basically about comparing two measurements, but in validity case, we compare technique A to a gold standard, which we consider the truth. And measuring validity is about quantifying bias and systematic error of the technique A. In contrast, the reliability is about comparing technique A to a repeated measure B to quantify random error. For example, we comparing mammography with histopathological tests to diagnose breast cancer. So it is an example of validity study. If we comparing two 24-hour diet recon in weekdays, that means we are conducting a reliability study. So for discrete variables, we can use Spearman correlation, percent agreement, percent positive agreement, kappa statistic to assess validity and reliability of these techniques. Only in validity study, we can calculate the sensitivity and specificity of the measurement. For continuous variables, we can use Pearson correlation and Spearman correlation, regression, scatterplot, Bland-Allman plot to assess both validity and reliability. But only in reliability we can calculate the coefficient of variation. We can look into this technique, the measurement in the next slides. First, let's talk about correlation, which can be calculated from both discrete and continuous measurement. Correlation is a measure of association that indicates the degree to which two variables have a linear relationship, and it can range from -1 to +1. If it equal to 0, It may indicate that there is no correlation between two variables. However, we need to interpret the correlation coefficient with caution. We can go to the next slide to see why. Here is an example correlation in a validation study. The author took an example of participants in non-health surveys, and then they estimate the serum creatinine level in their stored blood sample using a gold standard technique called CCRL. In this figure, we can see that the correlation between the two measurements are very high. The correlation coefficient is 0.95, which is very close to the perfect correlation. However, the line of best fit is a little bit different from the line of agreement. Therefore, the author concluded that the serum creatinine measure in the non-health survey is very reliable. But by us, in this case, the Pearson correlation is kind of sensitive with reliability but not validity. In the figure on the right, we can see that with the same value of correlation coefficient, we will see different pattern of relationship between the two measurements. Sometimes if the relationship between the two measurements are not linear, the correlation coefficient can be 0, but we can see that there are still some relationship between the two measurements. So we need to be careful and be sure to check the scatter plot to see the relationship between the two measurements before we interpreting the correlation coefficient. So percent agreement and percent positive agreement are only used for discrete measurement because they are percent. So percent agreements is a proportion of individuals who are classified the same by both tests. You can see the formula on the right. We take the sum of people who got positive and negative on both test 1 and test 2 to see how they contribute to the total number of patients who are tested. The issues of percent agreement is that in the case of rare disease, we got only very small amount of people who got positive on both tests, but we got a large amount of people who got negative on both tests. So in this case, we should calculate percent positive agreement. We will remove the individual who got negative on both tests from the numerator to see the positive agreement. So what if the agreement is just by chance, like 50%? What should we do in this case? A better measurement of validity and reliability is kappa statistic. We will see the difference between observed agreement and expected agreement by chance alone. Normally, higher value of kappa will show a better agreement between two measurements. This is an example of kappa statistic. In this example, we have a student reviewed the liver ultrasound twice, and then for each review, we ask the student to rate the brightness of liver into 4 categories: normal, mild, moderate, or severe. And then we can create a table like this to show the agreement and disagreement between the two reviews by the same student. The green cell shows the agreement of the two reviews of that student by summing up the number in the green cell and divide it by the total of review. We can get the observed agreement. To calculate the expected agreement, we need to calculate the expected count by multiplying the proportion in row with the proportion by column, and then multiply it with total. And then we will summing up all the expected count in the green cell and divide it by the total to get the expected agreement. Using the formula in the previous slide, we can calculate kappa. In this case, we see that like comparing the observed agreement with the expected agreement by chance alone, the kappa is equal to 0.55, which show moderate agreement between the two measurements. Next, we talk about sensitivity and specificity, which are only used to measure validity. So sensitivity is the proportion of actual positives that are correctly identified as such. For example, the percentage of sick people who are correctly identified as having the condition. So specificity is the proportion of actual negatives that are correctly identified as such. For example, the percentage of healthy people who are correctly identified as not having the disease. Positive predictive value is the proportion of persons with a positive test result who are identified as having the condition by the gold standard test. Negative predictive value is a proportion of persons with a negative test result who are defined as not having the condition by the gold standard test. Scatterplot is a very useful measurement to evaluate the validity and reliability of two continuous measurements, and it should always come with the correlation coefficient. Another famous figure to show the validity and reliability of the test is bland and bone plot. So we will plot the difference between two measurements against the mean of two measurements, and then we will add a zero line and then the two limits of agreement line. The limit of agreement is calculated by the mean difference plus and minus the two standard difference, and the closer the dot to the yellow line will show the higher validity or reliability of the test. The coefficient of variation is only used to assess the reliability of continuous measurements. It is calculated by dividing standard deviation of replicates by mean of replicates. It shows how the distribution of values for a measure depends on the mean and the random error. So the lower CV percent, the higher reliability of the test is. In epidemiologic study, we usually want the correlation of variation below about 10%, but for laboratory study, which may require higher reliability, we may require the coefficient of variation below 3%. So we talk a lot about what validity and reliability is and how can we assess these two concepts. And we also can feel that like the measurement error and misclassification can influence validity and reliability. And the source of error can come from person, intra-person or inter-person, or it can come from measurement tool or observer, or during the data entry, during the recording of measurement. So what kind of strategies can we use to deal with the threats to validity? So at all stages of the research, we should try our best to protect the validity and reliability of our measurement to make sure that we can measure what we want to measure. In the study design phase, before fully implement our research, we should conduct pilot study to explore possible errors, distortion from the initial proposal during sampling or selection or data collection, etc. In the data collection phase, we should regularly and randomly check the data collection process to detect and handle any distortion or bias from the proposal. And ideally, we should have independent assessment research at the same time to check and detect any systematic or random errors happen. And in the analysis phase, we should take into account all kind of confounding measure that we have, and we need to treat it by adjustment or stratification and acknowledge in the report. Some other detailed example of quality assurance and quality control could be building in reliability and validity studies into our protocol, introducing a control group who will not expose the risk factor or intervention to reduce the threat due to unexpected and confounding factors, and carefully design pre-testing the instrument to avoid any kind of distortion, train and retrain the interviewers, and standardize of interview techniques and tools such as questionnaires are also important in reducing this bias, and many other techniques from the field work to the analysis like stratification and matching for confounding factor during analysis of the results could be used to make sure that we can measure what we truly want to measure. So to sum up the presentation, I would like to present you with the 4 common scenarios in the epidemiological studies. First, the optimal scenario that we are always looking for is a valid and reliable results. That means we have no systematic and no random error in our measurement. However, in reality, we often see common scenarios, which is we still have some random error, though minimal, and we still have some small bias, but we cannot estimate those bias. A manageable scenario would be we have bias and we can estimate it and account it for it, and we know the magnitude and direction of the bias to evaluate and quantify and adjust it in our analysis. The most problematic scenario is that we have high level of random error and high level of bias we cannot estimate. In this case, I think that we should redo our study to avoid any kind of bias and unreliable findings. So thank you very much for your attention, and I hope that you can use this knowledge about variability and reliability in your study, in your work in the future.